Okay, as promised, here we are talking about shear stress. Okay, so we have a new equation. Looks kind of like normal stress, doesn't it? Except it's tau equals V over A. Tau that's the small, Greek letter tau. I'm going to go back and one more time. I'm going to draw my beam. Remember what happens when we cut the beam? You must have a M and V. Okay, here's my V, here's my N, there's my M, okay? The last video we talked about normal stress, now we're talking about shear stress. So what's the difference? Normal, right, is if I have a beam, I'll use my eraser, if I try to make it longer or shorter, right, that's normal stress. So what is shear stress? Well, if I have a beam and I have a downward force and I have an upward force, I'm trying to tear that beam in half, right? Almost like tearing a piece of paper, okay? So when you see shear, I want you to think tear, right? That means to just tear it in half this way, okay? And you'll notice that the shear force is going down. It's parallel to the cut end where the normal force was perpendicular to the cut, okay? So this is the force that's going to tear through something, okay? So you'll typically get this on problems like this where we have a beam and it's supported by a cable or a rod or something here. And we have a pin connection on this end, okay? And so what do we have here? We're asked to find the average shear stress in the 20 millimeter pins on the given beam. So there's a pin here at A and there's a pin right there at B. So we're asked to find the shear stress, the intensity of that force that's trying to tear those pins in half, okay? All right, so let's see if we can do this. My eraser left black crud on my board. Okay, now there's two kinds of shear stress, okay? Well, there's not really two kinds, it's all the same, but what you're gonna see is you're gonna see single shear or double shear. Whoa, that's not how you spell that. Double shear. Typically, those are the two things you're going to see, okay? So let me tell you about the difference in those. And then we have it right here on the board, okay? So single shear would be like, okay, I've got my little truss here. I'm going to bring it up here where you can see it. I've got a bolt through here. If I want to take this member right here and just tear it off, and just pull on, tear it off, how many times am I going to have to tear through that bolt to tear it off? Well, I just got to break it one time, right? If I just break it one time, it comes off. That's single shear. I only have to tear through one. How about this? Look how that's built. Do you see how that's built? So I've got two tabs here, and I've got a bolt going through both. If I wanted to tear this block off of there, can I just tear that bolt one time? No, I got to tear it through there, and I got to tear it through on this side, right? That's double shear. So I've got to tear it through twice. So in statics, we didn't care. You had a pin connection, it was a pin connection. That's all we know, right? But here, when we have a pin connection, we didn't know what kind of pin connection we have. So what we have here is kind of a blow up of what this pin connection looks like. Here's the beam, and here's the hinge, right? The hinge at A. Got a pin going through, so is that single or double? Again, if I pull on this guy, I've got to tear it through there and through there. That's a double shear. This one, if I pull on this, what is that? Well, if I just tear it right through there, uh-oh, I got my mark gone, then it's broken, it comes apart, right? That's single shear, okay? Now, what's the difference? What's the difference? Well, the difference is I can't find my purple pen, there it is this, okay? This is the equation for single shear, okay? Well, how's double shear different? Well, think about it. The force is the same. What's different? I got to shear through two cross-sectional areas. So it's simply this. Okay? This just tells me how many areas I have. And if I had something weird like a triple shear, I've never seen one, but I don't know. You put a 3 there. But there's your single shear. Here is your equation for double shear. Okay? And then I put V over A. A is the cross section of the thing that I'm shearing through, which would be the bolt or the pin. And then V is the shear force that's applied to that. So the very first thing I need to do, we need to do a bit of statics on this to determine what is the force at A and what is the force at B. Okay? So here we go. Let's see if we can do that. All right, we'll do some red reactions. So what do we have? Over here at B, I have, what is that? What is that guy? Remember from statics? Let's draw a new free body diagram. Okay? You know what that is? That's a two-force member. So here's what my free body looks like. At A, I have an AY and an AX. I have a 50 right there. That's kilonewtons. And then over on this end, I have a rod. Is it in tension or compression? And it's in tension, and tension members pull, don't they? Okay? We'll just call that, we'll call that BC. Okay? And let's see, if this goes to the right, AX must go to the left. Which way do you think AY goes? I think AY has to go up, don't y'all? Okay, so let's find out what all these things are, because that's going to be what the force. I mean, this pin right here at B, what's the force it's going to feel? It's going to feel that guy pulling on him, isn't it? What about over here at A, what's it going to feel? What if I find it has an AX and it has an AY, it has both? And I think I am, right? What if it has both? What's the magnitude of that force at A? Well, it's that squared plus that squared, square root, right? Remember that? We can handle it, can't we? All right, here we go. Let's take the moments at point A. Okay? Look here, another statics problem before I ever get to the solids part, right? So if I take the moment at A, that's all knocked out. The 50 rotates me counterclockwise, so minus 50 times how far away is that from A? 2 meters. Okay? And then this guy has two components, doesn't he? He's got one there and one there. What about that component? Cha-cha-cha. That gets knocked out, doesn't it? This, what is that guy? That guy is 4/5 of BC. Remember that from our 3, 4, 5 triangle. This is 3/5 BC. That's 4/5 BC. So which way does that guy rotate me? He rotates me counterclockwise. That's positive. So plus 4/5 BC times how far away is that guy from A? 2 plus 4, 6. Okay? Hey, we can solve it, can't we? So 100 times 5/4 divided by 6 is equal to BC. That was some algebra. I did all that in one step right there. Okay? Tell me what that is, handy dandy calculator. Okay. 100 divided by 6 equals times 5 equals divided by 4 equals 20.83. Equals 20.83 kilonewtons. That's the force in BC. Can we find AX? Well, that would just be the sum of the forces in the X. And so what do we have in the X? I have minus AX plus BC, which is 20.83 times 3/5. So AX is equal to times 3 equals divided by 5 equals 12.5. And then finally, the sum of the forces in the Y is what? AY minus 50 plus 4/5 of 20.83. So let's see. AY equals 50 minus what? 20.83 divided by what? Or let's just do times. Times 4/5 is what? 0.8. That'll get it, won't it? 33.33. So AY equals 33.34 kilonewtons. Okay? So now, I know the force acting here is 20.83. That's what's acting on BC. So that's the force that's trying to shear that pin in half. What's the force over here? Well, you know what? Let me draw AY this way. Still going up, right? There's AY. So here's what we know. If we take those two and add them together, we get this like resultant force there, right? That's the actual force at A. And how big is that resultant force? Well, it's 12.5, where's my square button, squared, plus 33.34 squared equals, and then the square root of that, of the answer, is equal to 35.61. So this is 35.61 kilonewtons, okay? So here we go. Now we can do the solids part. This is all statics. That's why I told y'all better sign up for this class after statics, right? Here we go. Tau, let's just call it A for pin A. Well, pin A is what? Pin A is a double shear, right? So here we go. What's the force at A? The force at A is 35.61. Now look what's going on here. This is in kilonewtons. What if I did this? What if I did this? Is this going to mess you up? I'm going to move the decimal over 3 places. 1, 2, 3. 35,610 what? Newtons. Why did I do that? Because I want to get it in a form I remember. Here's what I remember. Newtons over meters squared is pascals. Newtons over millimeters squared is megapascals. Okay, remember the extra M goes on the megas. So if I do this, right, what's the bottom going to be in? 2 times, what is the, what do we have here? 20 millimeter diameter pins. So that's a what? 10 millimeter radius. So pi times 10 squared, pi r squared, right? And that's going to be millimeters squared. So now what do I have? Newtons over millimeters squared, megapascals. You just got to get it where your units work out, where you understand what they equal, right? So that's why if I know if I have that form of theirs, all I have to remember, I'll move it around after I get my answer, right? So that makes a lot of sense to me. Okay, so 35,610 divided by 2 equals, divided by pi, where's my pi button? Pi equals, divided by 100 equals 56.68. So 56.68, and what is that unit? Well, that's megapascals, right? Because it's newtons over millimeter squared. Okay, so that's what's going on at A. Remember the 2, okay? So what's going on at B? Well, B is, what's the force at B? He's feeling that. So 20.830 newtons. That's in kilonewtons. I'm going to move my decimal over 3 places. Remember, kilo is 10 to the 3. What's 10 to the 6? Mega is 10 to the 6. What's after that? 10 to the 9th. What's that? That's giga, right? Like gigapascals. You could have that, right? You got to remember that stuff right there. I know if you're from another country, metric system is natural, but to us Americans, we haven't switched over yet. I don't know why, because it makes a lot of sense. Okay, so now I'm doing single shear. I'm doing B at single shear. I'm just V over A, so I just need 1A, which is pi r squared, millimeter squared. So again, I'm going to have newtons over millimeter squared, so 20.830 divided by pi equals, divided by 100 equals 66.330. Okay, so there is what's going on. That's the shear stress at point B. That's the stress it feels from trying to tear it in half. This is the shear stress at point A, okay? And that's how you calculate it and tell the difference between single shear and double shear. You got to know, it just can't be just a plain pin connection. You got to know, is it a single or is it a double, Okay, and they're going to tell you some information about that when they give it to you. Okay, I hope this makes a lot of sense. See you next time.